To understand the limits of our power grid, we have to look at what happens when the Earth turns against it. When a severe geological event strikes, the physical arteries connecting a community to the broader macrogrid are severed. For decades, utility engineering has prioritized reliability. The goal is straightforward: minimize the duration and frequency of routine outages. We measure this using indices like SIDI and SIFI. But these metrics track high-probability, low-impact events, things like a tree falling on a wire or an animal shorting a transformer. In the aftermath of a major earthquake or tsunami, routine reliability metrics are irrelevant. When coastal infrastructure is wiped away, the numbers stop mattering. This massive scale of destruction requires resilience. We define this as the grid's ability to survive the initial shock, operate autonomously, and sustain critical loads when the main grid is gone. Traditional distribution is centralized. A control room dictates commands to a passive network. When external communication lines are cut, the local system loses instructions. But a modern microgrid is engineered differently. It is a highly calibrated autonomous control system built for survival. To achieve resilience, local infrastructure must function as its own independent authority the exact second the external connection fails. At the exact millisecond a major fault occurs, a massive voltage sag propagates rapidly down the distribution feeder. Historically, safety regulations required anti-islanding. Any local solar array had to instantly trip offline to protect workers from unexpected currents. But as local generation scales, that logic creates a risk. If every solar inverter trips simultaneously during a voltage dip, the sudden loss of power can cause the entire macrogrid to collapse. The IEEE 1547-2018 standard changed the requirements. Now, distributed energy resources are legally mandated to actively support the macrogrid during an anomaly. This chart shows the required mechanism, the low-voltage ride-through curve. While older hardware would instantly shut down during a voltage drop, modern inverters track this curve and remain connected. They inject reactive power to pull the macrogrid's voltage back up. Once the microgrid fulfills its mandate to support the larger system, it evaluates the outcome. If the broader grid is still failing, the microgrid will activate its switches and isolate itself. IEEE 1547 transforms these resources into localized shock absorbers. They must endure the trauma to save the network before they are allowed to retreat to safety. The microgrid is now isolated, but the macrogrid is dead. The local system is standing in total darkness. It is a common misconception that possessing a large solar array guarantees backup power. Standard commercial solar inverters are grid-following devices. A grid-following architecture acts as a current source. It cannot generate its own voltage or frequency. It can only inject power by copying a pre-existing reference. The inverter uses a phase-locked loop to match the grid's rhythm. Without the macrogrid, it searches for a 50 Hz waveform that no longer exists, remaining paralyzed. True autonomy requires a grid-forming inverter. These act as primary voltage sources, creating grid parameters from scratch. This starts the black start process. The GFM autonomously energizes the local bus, establishing a steady 50 Hz heartbeat for the isolated network. Now, the paralyzed solar units detect that heartbeat. Their phase-locked loops lock onto the new frequency, transition online, and begin injecting power. Only after the solar generation is synchronized and supporting the battery can the heavy, critical motor loads be safely reconnected. Running purely on inverters changes the physics of protection. In isolated mode, fault currents are tiny, only 1.1 to 1.5 times the nominal current. Traditional overcurrent relays will miss the fault, requiring undervoltage or negative sequence detection instead. Without a grid-forming unit acting as the absolute phase leader, every other distributed energy resource is useless during a blackout. The microgrid is successfully running, but maintaining long-term survival requires a mathematical compromise. The battery energy storage system has two goals. It must save money during normal operations, but it must keep the grid alive during emergencies. This is a multi-objective optimization problem. Engineers balance a Pareto front, weighing cost savings against resilience readiness. Strategy 1 uses the battery aggressively for energy arbitrage, discharging it heavily during the day to offset peak pricing. If a major fault isolates the grid while the battery is at 20%, the system lacks the kinetic reserves to survive a load spike and collapses. Strategy 2 prioritizes the microgrid as an emergency reserve, holding 80% capacity while capping cost savings. By strictly holding 80% of its capacity, the system can confidently regulate frequency and absorb heavy load spikes during total isolation. Maximizing resilience requires a conscious, daily sacrifice of the battery's economic value. Tertiary control algorithms run continuously to navigate these nonlinear constraints, finding the optimal set point before disaster strikes. Resilience cannot be purchased at the moment of disaster. It is paid for every day through lower financial efficiency. We have built a system that rides through transients, establishes its own bus, and rations its energy reserves. But there is a final layer. Microgrids are cyber-physical systems, meaning the flow of electricity is dependent on data networks. This introduces vulnerabilities. If data packets are delayed, or if set points are manipulated, the system voltage and frequency will destabilize. Consider the ultimate stress test. The microgrid is operating in islanded mode, and the primary communication link to the inverters is severed. Without that link, the system loses its secondary control, the ability to coordinate the recovery of the frequency back to a perfect 50.0 Hz. However, the foundational layer, primary control, remains intact. The grid-forming inverters rely purely on terminal physics. Their droop control logic requires zero external data to function. The grid does not black out. It remains stable, though the frequency will safely settle slightly off nominal, around 49.6 Hz. By mastering inverter physics, the math of energy storage, and the boundaries of data reliance, engineers build a system capable of sustaining vital power even when the centralized grid is lost.